So just to demonstrate there's some technical points about the Fourier transform and the inverse Fourier transform. So I just sort of address those. And then the other thing I wanted to address is just to get some intuition about what to expect when we do a Fourier transform, and whether something makes sense or doesn't make sense. Because whenever you do these, like with a lot of computational things, whenever you do a Fourier whenever you do your computation, you're going to get an answer. Chances are you're going to get an answer. It's really whether it makes sense or it doesn't make sense. So you've got to be at a spot whether it makes sense or doesn't make sense. Okay. I need numpy because I'm going to do matrices times vectors. I want to plot, the time domain data and the frequency data, so I need to be able to plot. I got a couple of other libraries here, actually. So there's a package SciP that you probably know about. And that's one place you can find library functions for doing the Fourier transform. So that's why that's sitting in here. Although I'm not going to, firstly, we're going to program it ourselves. So sometimes we will, like with the ordinary differential equations, there are library functions to do that. We didn't all need to start programming it ourselves, but you learn a lot by at least first programming these things yourself. You get a better idea, I think, of what's going on, what to think about, what to worry about. So we're going to do that. There's one more little thing here. Seaborn is another package. I'm going to show you the matrix that we multiply. I'm just going to use kind of a heat map sort of plot that you can look at. So that's the only reason I've grabbed that. And there might have been better ways of doing that. Okay, so I'm going to imagine I've got some data that I've sampled in, say, the time domain, and there's eight data points, so 8 samples. And I'm going to just write my own Fourier transform code using matrix vector multiplication to calculate the corresponding version of this in the frequency domain. So the Fourier transform of this. So here's the number of data points, this uppercase N. Here's I just made up some data. So this looks like a kind of a square wave. So I've got 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. So I've got this little square wave thing. I need, for my matrix multiplication, I need to make some indices, a vector n and a vector k, that just count the array elements for me. So I made then here. So I just made, so lowercase n just counts from 0, 1, 2, 3, 4, 5, 6, 7. Lowercase k does the same, but one's a row vector and one's a column vector. So I can, multiply them together. And I've got to multiply them together in that when I calculate that matrix. I multiply them together when I form the matrix elements in the matrix. So these pair of lines here are just have a column vector and a row vector that count over the indices of my time domain data and my frequency domain data. Okay, then I'm going to use those to actually compute the matrix. So this is the computation of the matrix. So it's in this this is where Python's kind of nice. So it's just this one line here to compute a matrix. It becomes a matrix because I've got this product of columns of these vectors here. This is going to form a matrix. It's complex, and J is how we denote a imaginary number in Python. So this is going to kind of give me my matrix. I'm going to show you these heat map plots of this so we can get a better picture of it in a moment. And then my Fourier transform itself is just this little statement here. So this is the dot product of the data in the time domain, which is y, with the matrix, is going to give me the data in the frequency domain, and I'm just going to denote that uppercase y. And so that literally is the calculation of the Fourier transform. When I show you the plots, just to check things make sense, I'm going to Fourier transform it, inverse Fourier transform it. So take it back in the other direction and check at least that I get, when I go back from the frequency domain to the time domain, that I get what I started with. So I also have here the matrix that corresponds to the inverse Fourier. Yeah.
Oh, I just want to ask a question about syntax with the variable k up there. So you're not saying np dot reshape, but you're saying n, referring to the thing right before the variable before it, reshaping that. Is that how that works?
Yeah, I wonder if I think it'd be easiest to if I print these out. Would that help? Or maybe if I show you how the matrix gets formed by this, does that help?
Well,
The reason for that, and maybe that bit's not obvious, is somehow I've got to build a matrix by multiplying these together. You see in this line here, this has got to become a matrix.
so are you just turning one of them into a column vector and the other into leaving them as row vectors? So you can multiply them?
Yeah, exactly. So then, and I don't know if I can do that in the print statement. I wonder if I do. I doubt that this will work for me. Oh yeah, it did. So I think, does that explain it to you? I'm having trouble putting it in words.
My question was more about the syntax, though. I thought it should have said np dot reshape, but but no, you're telling it what it's reshaping, right? Like you're giving it a variable name and then dot reshape. Just the fact that it said n made me think it should have said np dot. Like, you know how every time we're pulling something from NumPy, you're saying np dot this thing, this function that you're using.
Yeah, let me go back to that. Oh yeah, that's it. This is reshaping n. It's not nump reshape. Okay. Yeah, that's what it is. Okay, that was a good question. So this last two lines is just where I'm going in the reverse direction. So I've got the matrix that represents the transformation from the frequency domain to the time domain. The only differences are, look, here's that normalization factor, 1/n. I've included that. And then the in the exponent, it's a positive exponent rather than negative exponent. And then I do the same kind of product of the matrix and the vector here to give me my vector now back in the time domain. I gave it a new name, a y prime. And so that's basically my my entire code here for doing the transform and going back again. So now I'm just going to make some plots. I got a lot of stuff here just to set up labels on things, but let's just go down to scroll down to the plots. And I got, maybe I'll show you these plots first. So this is actually the heat map of the matrix. And if I show you so it's complex. So I'm making a heat map of the real part here, and then I'll show you the imaginary part. So as I mentioned, if you think about the real part, the top row and the left-hand column, that's where it's e to the 0. So it's all real. So it's just a unity along the top row and the left-hand column. And then as you walk, say, along this second row, you're getting larger imaginary components. So we only get a fraction in the real of a real component, and then it essentially here is vanished. And then we got, you know, a negative real number, and it's all real now, but negative, and so on and so forth. If you went down along this row below that, then it's advancing twice as fast. So this first step, we go to 0 rather than 2 steps to 0. And then instead of 4 steps to -1, it's just these 2 steps to -1. So the phase is advancing twice as fast. So that's that's just what the real part looks like. And if we were to look at the imaginary part, then this top row and this left-hand column, right? Those are all zeros because it's purely real there. And then we start to pick up imaginary pieces as we walk, say, across this second row. If you remember, if you went 2 steps over here, this was 0 in the real part. Now this is -1. And this one was 0 in the real part. It's now -1. It's all imaginary. So that's what the matrix looks like. Okay, so now let's just look at this plot here. On this plot here, in the top left corner over here, this is the original signal. This is the time domain signal. So I label it Y subscript N. And if you remember, it went 1 -1, 1 -1, 1 -1. So I got a little bar chart of that. In the bottom left side, this is the result of doing the transform to the frequency domain and then the transform back to the time domain. So I should get back what I started with. And this is also, you know, that square wave, 1 -1, 1 -1 bar chart. So in that level, it did work. Over here on the center and on the right, I've got, so this is an interesting point. Normally we'll deal with real signals. And so I started with a real signal, I ended back up with a real signal. But because of the, you know, we're multiplying by complex matrix to do the decomposition into frequency space. In the frequency space, it would generally be complex, the uppercase Y. And so I'm going to plot both the real and the imaginary components of uppercase Y, the frequency domain version of the data. And so this top plot here in the middle, that's the real part. I should have labeled that, but this is the real part of uppercase Y. And this lower plot here is the frequency, is the imaginary part. So that's the first thing that I wanted to mention. So that's important now when you think about the in the frequency domain. In general, you're going to have complex uppercase Y, going to have real imaginary components. There's another couple of important parts about it. What the indices from 0 to 7 actually mean. And so that's important to understand that. So firstly, this first for k equals 0. K equals 0 corresponds to any constant time independent. That'll be non-zero if there's a constant or time independent offset in your data. So that's the frequency, 0 frequency component is in that k equals 0 bin, that k equals 0 sample. Our particular signal here, is going +1, -1, +1, -1. So on average, it's centered around 0. So it has no 0 frequency component. Then we got 7 other points. So the highest frequency you can see in discrete data is called the Nyquist frequency. And that frequency corresponds to a period that is 2 cycles. Two samples. So you're supposing we've taken 8 samples. The highest frequency that you could see, or the shortest period that you can see with that, is actually just 2. The period is 2 samples. So you can't see shorter periods of that or higher frequencies of that. If you had a higher frequency or you had a shorter period, in general, it gets aliased to a longer period or a lower frequency. So there's a limit. If you've got discrete data, there is a limit of what's the highest frequency, what's the shortest period you can see, and it's the size of 2 samples. So in our data, the limit of the frequencies that we can see corresponds to this sort of Nyquist limit of two samples. So we can see this because this frequency has a period of 2 samples, but it is actually the highest frequency we would be able to see in the data. So the way these 7 data points work here is that our high frequency that we can see, our highest frequency we can see is this one here. It's in this data point. A frequency that would be half that, so it would be 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. That frequency would be down here in this data point. The highest frequency here, the pattern of frequencies, the distribution of frequencies is mirrored either side of that highest frequency. So these 3 points here, 1, 2, and 3, which are the lower frequencies, are mirrored over here in 5, 6, 7. You'll see this more clearly when I show some other cases. So that's a second complication of interpreting this plot. Firstly, here's a special case. This is 0 frequency. In the middle of the remaining ones, there's the highest frequency. And on the right of that are mirrors of each other. So whenever you see a pattern over here through these bins 1, 2, and 3, you're going to see a mirrored pattern that's the same in 5, 6, and 7. Yeah.
So is the reason why our spike at 4 then because we have 4 instances of our repeating period?
Can you say that, repeat that?
Yeah, yeah, so like, you see that the only k value that we have, the yk at is 4, is that just because we have 4 repetitions of our up, down?
It's, no. It's because that is the frequency our frequency is 0.5 cycles per sample. So our period is 2 samples. Our frequency is 0.5 cycles per sample. And this corresponds to 0.5 cycles per sample. And that is actually the maximum. And that's why it's sitting there. To better answer your question, I think maybe I should have, I skipped one thing to begin with because I thought I'd come down to the plot and say it. I had this one other function call here. So when I'm in that central column, I'm plotting the time domain, frequency domain data versus the index k. And that's just going from 0 to 7. You can convert that with, for example, in the SciP library, or I think it's also a NumPy library, to the to actual frequencies. Actual frequencies in these units of cycles per sample. So here, I had imported the Fourier transform, the inverse Fourier transform, but also this thing that converts, this function that converts this index, which is a little hard to interpret, right, into frequencies in the units of cycles per sample. So here, you have to give it the number of data points that you've collected, but then it creates an array that has the same size as the number of data points, but now this array is in frequency. So that leads me to, I think by not very clearly explaining this, I made it that it is a little difficult sometimes to interpret this when you're plotting it versus index. But here I'm plotting the same frequency domain data, but now as a function of frequency. So in this particular plot, you see, we see this point here at 0.5, 0.5, that's 0.5 cycles per sample, which is the frequency of our data. In the middle of this plot is 0, which would be, if you had an offset, you'd see something there. The other interesting thing about this is that there's positive and negative frequencies. So what do positive and negative frequencies mean for our data? I don't think they mean anything for our data. If you've got real data, right, the negative frequencies would be an exact map of the positive frequencies. For us, there's no meaning to positive or negative frequencies, I think. Okay. Let me go back to, so I showed you my code that sort of did a simple forward Fourier transform and reverse Fourier transform. It checks out in that we got back what we started with. And I think it checks out too in that this data here, look, it has a single period in it, which is a period of two samples, which corresponds to this frequency of 0.5 cycles per second. Okay, so here is, I kind of summarized that version here, and to help, because, you know, as I say, it is a little, you know, confusing maybe to decode the meaning of the frequency domain data when it's plotted versus K, these little labels here tell you what the frequencies are in cycles per second. So this one where we see a non-zero value, that's half a cycle per second per sample. This is the zero, this is the offset. And then this group here and this group here are just the mirror of each other. So now I'll just show you quickly a few other cases. So now I've made the original signal, instead of having a period of 2 samples, it has this period of 4 samples. So it's like 1, 1, minus 1, minus 1, repeating. So now let's take a look at what we get in these plots. So again, this is the time domain data. I go to the frequency domain and then I go back to the time domain and I check that I get back what I started with and I get back what I started with. So that's okay. This is what the data looks like in the frequency domain. Maybe I'll look at over here where I've converted the horizontal axis from the index K to the actual frequency, and let's see what we see. Firstly, you see that there's kind of this mirror here about 0. You see that we've got one frequency in this, there's this mathematical fact that you've got positive and negative frequencies. For us, that doesn't really matter. We got one frequency that is 0.25 cycles per second. And so that's what we expect because our period is 4 samples. So we expect a frequency of 1/4 of a cycle per sample. So hopefully that makes sense. This is changing the period to be 2 times longer again. So now I've got 1, 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1. So I managed to fit 1 period in this region here. So what do we see in this case? So what we see is in this case is kind of interesting. So the last 2 cases, we just saw the frequency that was in the time domain. This is like a single frequency of the square wave. But why don't we see other frequencies? Because we said in that very first slide I showed you that a square wave is actually a superposition of many different frequencies. There's the lowest frequency, the sort of base frequency is the frequency of the square wave, but there are higher harmonics that make it a square wave, not a sine wave. Why didn't I see those when I went into the frequency domain? The reason I didn't see them in that case was that they were all, those harmonics, they're at higher frequencies. They were all higher frequencies than I can see in my frequency domain because they were above the Nyquist limit. So that's why I only saw the base frequency in the last 2. But now I've got a sufficiently long period or low frequency that I can start to see the higher harmonics that are part of a square wave. So if you look now, again, I'm going to focus on these plots over here on the far right because they're a little easier to determine. And I'm going to remind us that they're mirrored around 0. And I've got a frequency that is so this is 1/8 of a cycle per second. So both of these are 1/8, which is the base frequency. So 1 complete cycle is 8 samples. So this is the base frequency. But then I've got a higher harmonic. So this is 3 times that base frequency. And this higher harmonic are 3/8 cycles per cycles per sample. That's part of the sort of higher harmonics that will make would make this square wave out of sinusoidal functions. So I'm seeing that first harmonic. I'm not able to see those higher harmonics because, again, the Nyquist limit, I can't see it. Does that make sense? I just got another. Okay, here's an example where it's really, I just changed the phase of the original data. So I changed it by 90 degrees. So this data has the same period. It just sort of offset the phase of it. Again, I checked after I transformed frequency domain and back, I get the same data back. If we look over here, I get the same pattern of frequencies that are in the data. But one thing that's a little different, if I go back to, this one, has to do with the phases. So because I changed the phase of the signal, I've changed the phase of the data in the frequency domain. And so if I just flash backwards and forwards here, I still got the same frequency components, but I got a difference here in the phases. Oh yeah, I want to show. Okay, so this one also has that same period. But I got 1, 1, 1, 1, then 4 zeros. So it's a square wave, but it's not centered around 0. So this one we would think would have a 0 frequency component to it, compared to this one over here. So basically, this one here has some sort of overall offset. So that's what you see if you look in the frequency domain over here on the far right. I've got the frequencies that were 1/8 and 3/8 cycles per second, but I got one additional non-zero entry here, and this is at 0 frequency. This is because this data is no longer centered on 0. So that's why I'm saying that. And you see, I sort of wanted to show you this one because it lights up this 0 frequency for the index K. So you see it here. Okay. My goal in showing you those, I mean, it's in some sense a little bit silly to have 8 samples trying to fit things in that, but it kind of illustrates these features of the index K and what it really means. It's a bit subtle. And it illustrated kind of the effects of the Nyquist limit, right? And what we were able and were not able to see in the data. That's often quite important. Okay, the last few things I wanted to show you were, maybe I'll go to the code. Yeah, okay. So this is the second code I wrote. In this particular case, and I think when you're doing the assignment for this class, you probably want to do this. I made a user-defined function here in which I pass the user-defined function the array containing the data in the time domain, and it's going to return to me the data in the frequency domain. So if I want to call it many times, and actually part of the assignment will involve you timing it where you want to call it many times, it would be best to write it as a user function. but inside the user function is just the code I used outside the user function. So that's this guy here. Now I'm going to look at, you know, a more realistic sort of set of data where I got many samples. So I've got 1,000 samples now. And I'm going to put various categories of sort of shapes of data in that, functional forms of data in it. And so here, first of all, I'm going to fill it with a sinusoidal signal. And I think I've made the period here 100 samples. So I'm going to get 10 complete oscillations over the 1,000 samples. And we're just going to take the Fourier transform of that and take a look at that. So we do that. Here I'm, yeah. Well, let me do it with my function. This is the sci-p function. I'll do it with my function. And then I'm just going to plot the results. So let's just look at what I get out of this. Upstairs here is the data in the time domain. So we said that was just a simple sine wave, amplitude 1, 1,000 samples. That's the range, horizontal range of the plot, and it's going to be 10 complete cycles because I made the period 100. So that's the data I started with. And now I've got the data in the frequency domain where I'm plotting firstly in the red, the absolute value of that array uppercase Y in the frequency domain. Then I'm going to plot its real and its imaginary components. So this data here, if I look in the frequency domain, I've got this spike, sharp spike here. I see it in the absolute value. And I also see it actually in the imaginary component of the data, the frequency domain data. This looks like this is complicated in the real component, but actually look here, it's 0 essentially. So this is essentially 0. So what we're seeing here, you know, there's one frequency in this data. So I've got this nice pure sine wave. So I'm just going to see one frequency, not a whole array of frequencies like I would see with a square wave. And that one frequency, my period was 100 samples. And so the frequency is 0.01 cycles per sample. And that's where we see the spike. So this point here, the spike is located at 0.001, which is the frequency of my sine wave in cycles per sample. So this makes sense. It's all imaginary, it's not real, because of the phase of this data. If I was to change the phase of the original data, if I plot cosine, I would get, you know, it would be all real and 0 imaginary. Yes.
Above you do like a thing where you do division symbols, like in your.
Oh yeah.
What is it?
Let me explain that. So, because I didn't explain this little bit at all. In the previous example, I showed you the mirroring. In this example, this is what we often do in practice. Once we've seen that once, I don't want to see it again. So here, I'm firstly here I'm slicing. I'm slicing off the bottom half of the time domain of the frequency domain, keeping that. So I'm removing the top half, keeping the bottom half, because that's where one copy of the frequency spectrum is with the 0 frequency point. I had to do this because num-p, if you for division, will always return the result as a floating point number. And for slicing, I need an integer. And so if you do that double slash, then they'll return an integer for you. So that's the only reason for that. It's not like it is an integer, but I had to tell it to put it in integer. I also sliced this array of frequencies because I want to plot with that against that. And so I've got to chop off the top half of that and just keep the bottom half of that. So that's a common thing you'll see done when you use these library functions, for example, your own function, because of this mirroring in the frequency domain. So that's actually a good point, because that's why you don't see the mirroring here, because I just cut it off halfway through. Okay. So we talked earlier on, and we looked at some examples of square waves. Let's do the square wave case. Just take a quick look at that. So here's the square wave data. It's now my period is many samples, not just a few, one or a few, 2 or 4 or 8 samples. So I'm going to be able to see the different frequencies that make up a square wave. Yeah.
We have this spike where you in the second part we have this spike. So
I'm sorry, I couldn't quite catch that.
like in the second graph, we have that spike, right? Like
Yeah.
the data function.
Yes.
So is it because of the data or like what could be the
Yeah. Let me let me go through this. Okay, so this is a square wave, which we've said, and I think we probably understand from before, you can make a square wave from a superposition of many sine waves. There'll be a base frequency, which will have the same frequency as a square wave, and then there'll be higher harmonics that will turn the sine wave into kind of the square wave. So that's what you're seeing here. If you look at, let's look in the absolute value. First of all, this is the absolute value in the frequency domain. The biggest spike is at that 0.01 cycles per second. So that's the frequency corresponding to this square wave. That's the base frequency. So that produces a sine wave that, you know, is in phase with this. You see a whole array of other frequencies. So these are the ones that are going to turn the sine wave into a square wave. So this one here is at 0.03 cycles per second. Then there'll be one at 0.05, 0.7, 0.9 cycles per second. So it's all the odd harmonics of this base frequency. And you see their contributions are getting smaller and smaller. Their amplitudes are getting smaller and smaller. That's what's needed to make the square wave. So that's what you're seeing here. As to the real and an imaginary parts, where you see that this base frequency is mostly imaginary. As you move from the base frequency to the higher harmonics, the mix of imaginary and real components is changing. I don't have a wordy explanation of why it changes in this way. This is the way it has to change to make the square wave. So you're seeing what frequencies you need to make a square wave and what relative phases they need to make the square wave, and you're just seeing it in the Fourier transform. I'm not sure if I'm answering your question or not. I'll just show you another one or two here and then I'll quit because I've used up all the time. So this is kind of nice. There's in SciP, there's another kind of library or module that contains various types of signals. So there's a sawtooth in there. And here's the sawtooth. And again, you'd expect that this would be a superposition of many different sine waves, the base frequency and then various harmonics. And that's exactly what you see. Interestingly, now you see both the even and the odd harmonics in this. So it's a different pattern. It's a different mix of sine waves because it's a sawtooth, not a square wave. Maybe that's obvious. And I'll show you one last one. So this is just a function that gives an impulse. So there's just, this is like I mentioned earlier on, the delta function. So this is like a delta function. And what is the delta function made of? It's a little hard to see on some of this plot. If you look at the absolute magnitude, it's just one everywhere. It's made of summing up all the frequencies in this domain. So you put them all together. This real part here is just, you can't really tell from the plot, but it's just flipping from +1 to -1, +1 to -1. So the phases are flipping in the contributions of the different sine waves. The imaginary part here, it's all zeros. Again, I'm giving you no explanation of why it is exactly this pattern, but you're seeing how some really sharp signal in the time domain is spread way out in the frequency domain. And that's in general true, right? If you have a sharp signal in the time domain, it's going to have a lot of frequencies. If you've got a single sine, the reverse of this was kind of like the sine wave we started with. It's spread out in the time domain, but it's a single frequency in the frequency domain.